All right, so for chapter 5, we're going to look at solutions and reactions that happen in solutions. So some things that we'll look at, review from Intro Chem. This is where we're going to see molarity and double displacement reactions and other types of reactions that happen in water. Now, the solute and the solvent are the two components of any solution. There could be more than one solute, but typically we just do one solute, one solvent. The solvent is the one that's present in the majority, and the solute is what's present in the minority. And, in Intro Chem, we did all of our solutions assuming aqueous, right? AQ, which means in water. So if it's an aqueous solution, we know that the solvent is water. And then, of course, whatever is dissolved in that, like if we saw with our double displacement reaction, something like sodium chloride aqueous, that aqueous meant that the solvent was water, the NaCl would have been the solute. And of course, those two together, the sodium chloride and the water, together make up the solution. Now we can describe solution concentration, in other words, like how much solute is in that solvent, in a couple of relative terms. We can have dilute and concentrated. Those are obviously not, quantitative or numerical. It's just dilute means there's not a lot of solute dissolved in the solvent, and then of course concentrated means there's a lot more solute dissolved in the solvent. But if we want specific numerical concentration terms, the chemist's favorite, of course, is molarity, because it has moles in it, right? And we're used to knowing that moles is going to be our center point for all of our stoichiometry. So molarity is given an abbreviation of a capital M, and it is defined as the moles of the solute per liter of solution. So first question here is, let's calculate the molarity if we put 3.00 moles of potassium iodide in 2.39 liters of solution. So if we're finding molarity, we want to use the formula, moles per liter. And this one's very straightforward. We were given exactly the number of moles, and then we were given the liters. So basically, we're setting up a ratio. Sorry about that. If there's 3 moles in 2.39 liters, then how many moles would there be in 1 liter? And we get 1.26. And for your units, you can just use the capital M, or if you prefer, 1.26 and then mole per liter, right? And that would be the concentration of potassium iodide in this solution, all right? Now the next one, we're calculating molarity again, right? So we know that we're going to need moles per liter, but this time it says that we have 0.522 grams of HCl in 0.592 liters of solution. So for molarity, your solute has to be in moles, and because it's in grams, we're obviously going to need to convert grams to moles, and we remember that we use molar mass to do that. Some students like to go ahead and convert grams to moles first and then plug that into the formula and then take your volume into your denominator and then get your molarity. I try to do everything in just sort of one step if I can, or simplify it as much as I can. So whatever quantity of the solute I'm given, I go ahead and put that in the numerator, so 0.522 grams of HCl. And then my quantity, my volume in this case of the solution, 0.592 liters, I put in the denominator. And then I check my units. I've got grams per liter. I need it to be moles per liter, so I need a conversion step here that will get rid of grams of HCl and go to moles of HCl. Sorry, that didn't really come out very well. There we go. And of course, to go from grams to moles, I need the molecular weight or the molar mass from the periodic table. So if I add up a hydrogen and a chlorine, I get 36.46 using those atomic masses from the periodic table. So I'll take the 0.522, divide that by 0.592, and then divide that by 36.46. And if I keep 3 significant figures, I get 0.0242, capital M, for the concentration of the hydrochloric acid. All right. Now, that is when you find molarity. Those first 2 examples, we were asked to calculate the molarity of the solution. And if you're trying to calculate the molarity, you need to look at the formula, right? We need to take the moles of the solute divided by the liters of the solution. Now for question C, this one's going to be different because it says how many grams of potassium hydroxide are needed to make 2 liters of a 6.00 molar potassium hydroxide solution. And there should be a question mark there. So when molarity is given, I do this differently. I don't use the formula. Instead, I use it as a conversion factor. And this is sort of like what we saw with density. When you're solving for density, you need to take mass divided by volume. But if density is given, it can be used as a conversion between mass and volume. And that's exactly like molarity. If we're trying to solve for molarity, we need to do the formula, take moles divided by liters. But if molarity is given, we want to see that as a conversion step. And what that molarity tells us is that there are 6.00 moles of KOH, because that's the solute, in every liter of solution that we use. So if you look at this, if I wanted to make 1 liter of solution, I would need 6 moles of KOH. I'm trying to make 2 liters of solution, so it makes sense I'm going to need 12 moles of KOH. And then the question becomes, okay, well, what mass would that be? And we know that whenever we are given mass or we are asked for mass, we know we're going to need the molar mass from the periodic table. So molarity is going to be a conversion factor. When we start dimensional analysis, we always want to start with a mass or a volume. In this case, we're going to start with our 2-liter volume. And then that conversion step says, well, there should be 6 moles of KOH per liter, right? And if we're doing 2 liters of solution, we're going to need 12 moles. And then what I would do in this last conversion step is convert moles to grams using the molar mass. So potassium is 39.1, oxygen is 16, and then hydrogen is 1.01. So we get a molar mass here of 56.11 grams. So if I take that and multiply by my volume and my molarity and keep 3 significant figures, I get 673 grams of KOH. So the idea here is if I took 673 grams of KOH and I dissolved it in 2 liters of solution, my concentration at the end would be a 6 molar solution. Right? So that's molarity. Molarity, like I said, that is the chemist's favorite in terms of solution concentration. There are others. There's mass percent and volume percents and others. And we'll use those at different points for different types of colligative properties that we look at later. But for now, with stoichiometry, molarity is the favorite, of course, because it has moles in it. Now, if I took a 6 molar solution of KOH and I diluted it, by adding water, the solvent, obviously adding water will make that concentration decrease, right? If it becomes more dilute, the molarity is going to drop. And our formula for dilution is M1V1 equals M2V2. And basically what this is saying is my initial molarity times the volume that I use of that initial solution is going to be equal to the molarity after dilution and the total volume after dilution. And if you think about it, why does that work? Well, we're adding the solvent, but the solute inside isn't changing, just the concentration is changing. So my moles of solute that are present initially, they're the same as what's present at the end. The only thing I've added is the solvent, not the solute. So adding or could be taking away the solvent just changes concentration, but the moles of the solute remains unchanged. So that formula, M1V1 equals M2V2, is our formula for dilution, not our formula for stoichiometry. A lot of times students want to use that formula for stoichiometry, and you can't, because a lot of times your mole ratio of your A and your B, your 2 substances, is not 1-to-1. If your mole ratio is 1-to-1, then you could use it. And of course, when we get there, I'll explain that. But for now, just make sure M1V1 equals M2V2 is your formula when you're diluting a solution. And what you look for to know that it's dilution is there's only going to be one substance in the question. We're not doing any kind of chemical reaction. We're just changing the concentration of the hydrochloric acid, for example, by adding water to it. All right. So on the next page, we have an example that we can look at. It says, how many milliliters of a 10.15 molar sodium hydroxide stock solution would be needed to make 15 liters of a 0.315 molar NaOH solution? So stock solutions are often concentrated solutions. So like when we order chemicals from Fisher Scientific, let's say I need to order some hydrochloric acid. And I need, for my lab, I need to have a 0.5 molar hydrochloric acid solution. I'm going to make the 0.5 molar myself. I'm not going to buy it specifically from Fisher because then I'm just paying for them to ship me water. I'll buy the stock solution, the concentrated hydrochloric acid, and I'll dilute it myself, right? So what we're looking at is we want how many milliliters of a 10.15 molar sodium hydroxide stock solution. So this is my initial concentration, and my initial volume is what I'm solving for. And I'm looking to make 15 liters of a 0.315 molarity solution. So as long as you keep your pairs together, right, this volume goes with this molarity and this volume goes with this molarity, it wouldn't matter if you had this as V2 and M2 and the other one as V1 and M1. That doesn't matter. Your pairs just have to be correct. So 15 liters of 0.315, that's a set, and unknown milliliters of 10.15, that's another set. So basically, I'm going to take some small amount of this stock solution, dilute it to a total volume of 15 liters, and get the concentration down to 0.315. So how many milliliters of that stock solution will I need to do that? Now, the other thing I mentioned earlier is you can tell that this is dilution because there's only one substance here. It's just sodium hydroxide. There's no chemical reaction taking place. We're just taking a concentrated sodium hydroxide solution and diluting it to a less concentration sodium hydroxide solution. So when I plug in my formula, M1, 10.15 molar, V1 unknown, equal to M2, 0.315 molar, times V2, 15.0 liters. All right, so I've got my formula. I'm going to divide both sides by the 10.15 molar. The unit of molarity will cancel out, and then the unit of volume that I'll get for my answer is going to be in liters because my V1 unit was in liters. Keeping three significant figures, 0.466 liters. So about half a liter of that stock solution. If I dilute it down to 15 liters total, so I'm adding, basically 14.5 liters of water, I'll get my concentration down to 0.315. All right, that is a good place for me to stop for this first video.